Okay, sample problem 8.5. Hydrofluoric acid is HF, has several important industrial applications, including the etching of glass, manufacture of electronic components. Burns caused by hydrofluoric acid are unlike any other acid burns and present unique medical complications. HF solutions typically penetrate the skin, damage internal tissues, including bone, often with minimal surface damage. Less concentrated solutions can actually cause greater injury than the more concentrated ones by penetrating more deeply before causing injury, thus delaying the onset of symptoms and preventing timely treatment. Determine the magnitude of the partial positive charge and the partial negative charge on the HF molecule. Okay, so a lot of intro into what the molecule is, but the point is, here's HF. And let's get the information. This is from your textbook from table 8.5. First, we need the bond length. Now, in your textbook, the bond length, which we'll call R, is given in angstroms. Okay? So I'm going to write that information down. And then the actual dipole moment is given. But the dipole moment, mu, is given in debye. So it's 1.82 debye. So here's the logic. The dipole moment tells us the charge on the atoms, on each atom, times the bond length. So we're going to use the bond length and the dipole moment to find the charge. Once we got the charge, then that's our answer. The only issue here is there's some dimensional analysis to do. We just have to change units. But the dipole moment is equal to the charge on the atom times the bond length. Okay? The dipole moment and the bond length are both vectors. Okay? So here's what we do. We want to know what the charge on each atom is. So Q is the dipole moment over the bond length. So the problem is they give it to us in debye. So what I'm going to do is I'm going to convert 1.82 debye into coulomb meters. Okay, so here's the conversion factor. It's in your textbook. That's 1 debye. Okay, so we got to do that conversion. All clear. 1.82 debye times 3.336 times 10 to the minus 30. Oops, calculator didn't like that. So let's try it again. 1.82 times 3.336. 6.071. 6.072 actually. Times 10 to the minus 30. And then the debye cancel and you got coulomb meters. Okay? So now, what about this issue of the bond length? The bond length is in angstroms. So the conversion factor is, we have 0.92 angstroms, and 1 angstrom is 1 times 10 to the minus 10 meters. So that would be 9.2 times 10 to the minus 11 meters. So now we have it in meters. Okay? So now we can do the division here. 6.072 times 10 to the minus 30 coulomb meters over 9.2 times 10 to the minus 11 meters. Meters cancel, and that'll give us the charges in coulombs. So 6.072 divided by 9.2. 0.6599. Let's go ahead and round it to 0.660. And then let's do the powers of 10. Negative 30 minus a minus 11 is negative 30 plus 11, so that's negative 19, right? And then the units are in coulombs. Okay, so that's the charge on each atom as a factor of coulombs. But let's do this. we generally think of charges as being +1 or -1. That, when we say +1 or -1, we're doing it relative to the charge of an electron. So here's what I'm going to do. 1 electron charge is negative 1.602 times 10 to the minus 19th coulombs. So here's what I'm going to do. I'm going to take our charge in coulombs. Notice I haven't put it in scientific notation. We don't need to yet. And then I'm going to convert that to electron charges. Okay, now the coulombs cancel, and that gives us electron charges. So the 10 to the minus 19 is going to cancel. So it's 0.660 divided by 1.602. And you get 0.41. Okay, so that's the charge relative to the electron. So here's what happens. The H and the F are both going to have the same charge, but the more electronegative atom will have the negative value. So it's around 41% the charge of an electron. And then this would be plus 0.41. Okay, remember they have to add up to 0, so they have to have opposite charges. But that's very useful. What that tells us is the amount of charge on the hydrogen is about 4/10, 0.4, that of the charge of a proton. And the charge on the fluorine is negative 0.4. That's about 4/10 of the charge of an electron. It's kind of cool. So there's our calculation of the partial charges. Those are called partial charges. It's the amount of charge on each atom in that bond.